2,000 years before Newton, a man walking 14 miles a day through the Mediterranean dust just accidentally laid the groundwork for integral calculus.
Which is wild, right?
It really is. And then, he mapped the cosmos without a telescope. And just to cap it all off, he mathematically proved that the entire purpose of human existence is pleasure.
Yeah, it is a resume that fundamentally defies how we structure knowledge today. I mean, we live in a world of hyper-specialization,
Well, absolutely.
where, like, a biologist might spend their entire career studying just the acoustic mating calls of a single species of frog. Or a mathematician might devote 40 years to a single topological conjecture.
We really do like our experts confined to their specific disciplines.
We do, but when you stepped into the intellectual landscape of the ancient Mediterranean, that modern specialist model just completely shatters.
It totally does. So today's deep dive is an exploration into a mind that just refused to be confined to a single intellectual discipline. We are unpacking the life, the travels, the math, and the philosophy of Eudoxus of Cnidus.
Arguably the ancient world's greatest unsung genius.
Exactly. And we are piecing his reality together from ancient historical fragments, surviving commentaries from later mathematicians, and philosophical texts like Aristotle's Nicomachean Ethics.
And our mission for you, the listener, is to understand how one ancient thinker managed to connect the dots between practical medicine, pure mathematics, celestial mechanics, and human ethics.
Right, and more importantly, to see how his approach to problem solving, this relentless, unbounded synthesis of information, is basically a masterclass in cutting through our own modern information overload.
So Eudoxus lived roughly between 390 and 340 BC. But to understand him, you really have to understand that he wasn't operating in a vacuum.
He wasn't just sitting alone in a room somewhere.
Not at all. The ancient Mediterranean was this vibrating, interconnected web of knowledge. You had distinct schools of thought geographically separated by seas and mountain ranges, but they were still intellectually engaged in this massive conversation.
A centuries-long conversation. And Eudoxus was perhaps the most active participant in it. Let's start with where he's from. Cnidus, or Knidos, located on the Dasa Peninsula in southwest Anatolia.
Which is modern-day Turkey.
Right. And even his name feels like a spoiler for how his life would turn out. Eudoxus. It translates roughly to honored, or of good repute, from the Greek euou, meaning good, and doxa, meaning opinion or fame.
And it is a name he absolutely lived up to. Cnidus itself was a really fascinating place to be born. It was a Dorian Greek colony, incredibly prosperous, and situated right on major trade routes.
So a lot of ideas flowing in and out.
Exactly. But crucially, Cnidus was renowned across the ancient world for its medical school. It was one of the two great medical centers of the time.
What was the other one?
The other being on the nearby island of Kos, which is actually where Hippocrates was from. So Eudoxus is born into a culture that deeply, deeply values observation, biology, and the practical mechanics of the human body.
But he doesn't just stay there and become a local doctor, right?
Yeah. No, not at all. The historical records paint a picture of a man who was inherently restless. He was a true knowledge hunter.
So where does he go first?
He starts by heading west to Magna Graecia, which are the coastal areas of southern Italy that were heavily colonized by the Greeks. And he goes there to study mathematics under a man named Archytas.
Archytas. He was a pretty big deal, wasn't he?
Oh, an absolute giant of his era. He was a statesman, a philosopher, and a brilliant mathematician belonging to the Pythagorean school.
The Pythagoreans, okay. We will definitely be coming back to them.
We certainly will. But Archytas was arguably the first person to actually apply mathematical principles to mechanics. So by studying under him, Eudoxus is being steeped in the most rigorous, advanced numerical theory on the planet at that time.
So he's learning to see the world not just as biological tissue, like he learned back in Cnidus, but as a system governed by strict rational proportions.
Exactly. But he doesn't stop there. He then heads over to Sicily to study medicine under Philiston, sort of blending that high-minded Italian mathematics with Sicilian medical practicality.
It's like he's collecting these disciplines. But the real turning point, the moment where you realize just how fiercely dedicated Eudoxus is, happens when he is 23 years old. He travels to Athens.
And Athens, even though they had lost some of their political empire after the Peloponnesian War, Athens was still the undisputed intellectual capital of the ancient world.
It was the home of Plato, the gathering place of the sophists, the epicenter of philosophical debate.
Right. And he travels to Athens with a physician named Theomedon. Theonon is essentially acting as his patron.
Now, some historical sources suggest they may have been lovers, which was a deeply embedded social dynamic in ancient Greek intellectual circles.
Yes, exactly. The older established figure would provide financial support, social introduction, and mentorship to a promising younger man. So Theomenon gets Eudoxus to the greater Athens area.
But they don't live in the wealthy city center.
No, they settle in Piraeus, which is the port city on the coast.
Piraeus was a bustling, chaotic, working-class naval hub. It was noisy, filled with sailors, merchants, the smell of the sea.
It was a very, very different environment from the serene, shaded groves of the philosophical academies in Athens proper.
And this is where the physical reality of his life really hits me. Eudoxus is living in Piraeus, but he is determined to attend the lectures of the sophists and the philosophers in Athens.
Which is not a short trip.
Right. The distance from Piraeus to the heart of Athens is roughly 7 miles. So every single day, Eudoxus walks from Piraeus to Athens, listens to the greatest minds of his generation, debate rhetoric and philosophy, and then walks 7 miles back.
14 miles a day, on foot.
That's like walking a half marathon every single day just to audit a college class.
It really is. And if you imagine the Mediterranean climate, the sheer physical toll of a daily 14-mile commute on ancient dirt and gravel roads and sandals through the heat and the dust, it's staggering.
It really speaks to a level of internal drive that is difficult to comprehend today. He is literally exhausting himself physically to build this massive, multidisciplinary database in his mind.
It's the ultimate contrast to the image we often have of the wealthy aristocrat just casually pondering the universe over wine. This is manual labor in the pursuit of philosophy.
But it does raise a question about his resources. Was he just a wealthy, ancient tourist? Because if he's relying on Theomenon just to get to Athens and living in the port city, he clearly isn't independently wealthy.
That's a great point, and it becomes a major plot point in his life shortly after his time in Athens.
How so?
Well, Eudoxus returns home to Cnidus. He has absorbed the mathematics of Italy, the medicine of Sicily, the rhetoric and philosophy of Athens, but he realizes there is a massive gap in his knowledge, and in Greek knowledge in general.
Which is astronomy.
Exactly. He knows that to truly understand the heavens, he has to go to the oldest, most advanced astronomical center in the world. He needs to go to Egypt.
But he's broke.
He is broke. He has the ambition, he has the intellect, but he lacks the capital entirely.
So how does a guy with no money manage to keep funding this pan-Mediterranean education?
What happens next is a testament to the sheer force of his reputation. His friends, his fellow citizens in Cnidus, and various supporters recognize that Eudoxus is a generational talent.
Right, they see the potential.
They look at the work he has already done, they remember the discipline of a man who walked 14 miles a day for his education, and they essentially pool their resources. They crowdfund his journey to Egypt.
It's a literal ancient GoFundMe.
It really is, and it tells us something vital about the culture of ancient Greece. There is a profound societal value placed on intellectual achievement.
These friends didn't invest in Eudoxus expecting a financial return.
No, they invested in him because they believed his mind could unlock the secrets of the universe and that the glory of his discoveries would reflect back on all of them and their city.
That is so cool. So the ancient GoFundMe succeeds, and Eudoxus secures passage to Egypt.
Yeah.
Specifically, he goes to Heliopolis, the city of the sun, which was a major religious and scientific center.
And he stays there for 16 months.
Now, 16 months might not sound like a lifetime, but in the context of ancient Egyptian science, what is he actually doing there?
He is tapping into an astronomical tradition that was millennia old at that point. You see, the Greek approach to the sky up to that time was highly philosophical.
Mostly just theories and ideas, right?
Exactly. But the Egyptian approach was deeply empirical and observational. The priests at Heliopolis had been keeping meticulous records of solar alignments, stellar risings, and lunar cycles for literally thousands of years.
They just had continuous, unbroken data.
Exactly. So Eudoxus, with his rigorous mathematical mind trained by the Pythagoreans, is suddenly given access to this vast ocean of observational data.
That must have been like a kid in a candy store for him.
Oh, absolutely. He is learning their techniques for tracking the sun, understanding the exact length of the solar year, and mapping the constellations.
And then he takes that ocean of data and he just keeps moving. He leaves Egypt and heads north to Cyzicus on the Sea of Marmara. He travels south to the court of Mausolus in Canaria.
And everywhere he goes, he isn't just learning anymore. He's teaching. He is gathering his own students, forming his own school of thought.
He's becoming a master in his own right. And then, around 368 BC, he makes a triumphant return to Athens.
This return to Athens is incredibly symbolic. He arrives not as a poor student commuting from the port city, but as a renowned polymath accompanied by a retinue of his own students.
The historical fragments suggest that his intellectual authority was so respected that he actually took over the administration of Plato's academy for a period while Plato was away in Syracuse.
Yes, the intellectual gravity in that room must have been dense enough to bend light, because among the students at the academy during that time was a young Aristotle.
Wait, really? Eudoxus is teaching Aristotle?
The pedagogical lineage is breathtaking. The transmission of ideas from Socrates to Plato to Eudoxus to Aristotle.
That is incredible.
And Eudoxus introduces a level of rigorous mathematical methodology to the academy that deeply influences Aristotle's later insistence on logical deduction and empirical observation.
After this incredible sprawling journey, Eudoxus finally goes back home to Cnidus. But he doesn't just retire to a villa to write memoirs.
No, he embeds himself completely into the fabric of his city. He serves in the assembly as a lawmaker, literally writing the legislation for his people.
And he builds an astronomical observatory so he can continue the work he started in Egypt. And he raises a family, a son, Aristagoras, and 3 daughters, Actis, Philtis, and Delphus.
It is the arc of a life fully lived. He went out, gathered the fragmented knowledge of the known world, synthesized it, and brought it back to enrich his community.
But if we really want to understand the mechanics of his genius, how a guy who walks 14 miles a day applies that relentless, grinding dedication to a problem, we have to look at what he did to mathematics.
Yes, because when Eudoxus was coming of age, Greek mathematics was not just stuck, it was in the middle of a catastrophic existential crisis.
The irrational crisis. This is where the history of math reads like a psychological thriller.
It really does. What's fascinating here is the absolute panic it caused. To understand why Eudoxus had to save mathematics, we have to talk about the Pythagoreans.
Right. Eudoxus's teacher, Archytas, was a Pythagorean. And the Pythagoreans didn't just study numbers, they literally worshipped them.
Worshipped is not an exaggeration. The Pythagorean school, founded by Pythagoras of Samos in the 6th century BC, operated almost like a mystic religious cult.
They were pretty intense.
Very intense. Their fundamental axiom was all is number. To them, the universe was not made of earth, air, fire, and water. It was made of whole numbers, integers, and their ratios.
The rational numbers.
Correct. They believed that everything in the cosmos, from the harmony of a plucked lyre string to the orbits of the planets, could be perfectly described by comparing whole numbers.
So if you have 2 lengths of string or 2 plots of land, you could always find some tiny common unit of measurement that would fit perfectly into both of them a whole number of times.
Exactly. It is an incredibly comforting worldview. It means the universe is neat. It means there are no messy edges, no infinite remainders.
Everything is commensurable. Everything can be measured by a shared standard. Arithmetic was the supreme divine truth of reality.
But then, the Pythagoreans made a discovery that absolutely shattered this comforting worldview. They were studying a simple square.
Just a normal square.
Just a square where each side is exactly 1 unit long. They wanted to calculate the length of the diagonal line cutting across that square.
Using their own Pythagorean theorem, a squared plus b squared equals c squared.
Right, and they determined that the length of the diagonal is the square root of 2.
And the square root of 2 is an irrational number. It's 1.41421356. And it just keeps going forever.
It never repeats, and it never ends.
This realization must have been devastating.
It was. It meant that the diagonal of a square and the side of a square are incommensurable. They do not share a common unit of measurement.
So no matter how incredibly tiny you make your ruler, if that ruler perfectly measures the side of the square, it will never perfectly measure the diagonal.
There will always be a microscopic, infinite, messy remainder.
The universe wasn't neat and tidy after all. It had these gaping holes in it. And this wasn't just a rounding error. This was a philosophical catastrophe.
There's actually a legend that the Pythagorean who supposedly revealed this secret to the outside world, a man named Hipparchus, was thrown off a boat and drowned at sea by his fellow cult members.
Because the discovery was considered so dangerous to their theology, that is intense.
Whether Hipparchus was actually murdered over a math problem or not, the legend perfectly illustrates the panic. The discovery of irrational magnitudes broke the ancient idea of measurement.
It threw the entirety of geometric calculation into question. I mean, if you cannot measure 2 lines with a common unit, how can you compare them?
How can you prove that 2 triangles are proportional? How can you know anything for sure if the foundation of arithmetic is flawed? The Greeks called these incommensurable lengths allogon, which means the unutterable or the inexpressible.
So mathematics essentially grinds to a halt because they don't know how to talk about these unutterable numbers.
Yeah.
And this is where Eudoxus steps in.
Yes. He looks at this wreckage, at a mathematical system paralyzed by the infinite, and he does something revolutionary. He pivots entirely.
How so?
He realizes that trying to force arithmetic to explain continuous geometry is the problem. Arithmetic is discrete, you count whole things. Geometry is continuous, a line can be divided infinitely.
So Eudoxus shifts the entire focus of Greek mathematics away from numbers and arithmetic and toward pure geometry.
Exactly. He introduces the concept of non-quantified mathematical magnitude.
Okay, we need to break this down for the listener because this is the breakthrough that saves math.
Hmm.
What exactly is a non-quantified mathematical magnitude?
He essentially declares that we do not need to know the exact numerical value of a line or a surface or an angle in order to work with it logically. A line is just a magnitude. It isn't a number.
Oh, I see.
And he establishes a completely new way to define proportionality that does not rely on a common unit of measurement. He creates a framework where a ratio isn't a fraction or a numerical value. It is a primitive structural relationship between two geometric magnitudes.
To make this practical, imagine you are an ancient merchant, and you are trying to compare the purchasing power of two totally different currencies. Let's call them currency A and currency B.
Okay, I'm with you.
You have absolutely no idea what the exact exchange rate is. You have no universal standard, no gold standard to measure them against. They are incommensurable.
Right.
But you can look at what baskets of goods you can buy by scaling up the amounts of each currency. You can say, I don't know the exact math, but I know that if 3 bags of currency A buys me more amphorae of olive oil than 4 bags of currency B, then I know for a fact that 6 bags of currency A will buy me more olive oil than 8 bags of currency B.
Precisely. You are establishing a rigorous, provable relationship between the two currencies without ever knowing their exact numerical value. You're comparing relationships of scale.
You're comparing relationships, not raw numbers.
And by creating those currency baskets, Eudoxus was able to build an airtight, logical definition of proportionality that bypassed irrational numbers entirely.
It's so clever.
His actual definition, which forms the core of Book V of Euclid's Elements, is a masterpiece of abstract thought. He stated that if you have 4 magnitudes, let's call them A, B, C, and D, you want to prove that the ratio of A to B is exactly equal to the ratio of C to D.
How do you prove they are equal without dividing them?
You take any 2 positive integers, let's call them multiplier m and multiplier n. You multiply a and c by m. You multiply b and d by n. Eudoxus declared that if m times a is greater than n times b, then m times c must be greater than n times d.
Wow, okay.
If it is equal, the other must be equal. If it is less, the other must be less. And crucially, this relationship must hold true for every possible integer you could ever choose for m and n.
Wait, for every possible integer.
That is the genius of it. He uses the quantifier for every. By demanding that the relationship holds for every conceivable multiplier, Eudoxus is harnessing the concept of infinity.
He is boxing in the irrational number, trapping it between rational scales.
Exactly. This is a direct ancient precursor to the rigorous epsilon-delta definitions of limit and continuity that were developed in the 19th century for advanced calculus. Eudoxus provided a flawless, explicit set of axioms to handle a continuum of quantities.
It is an incredible intellectual leap. He builds a bridge over the abyss of irrational numbers so Greek mathematics can keep marching forward.
He really did.
But there is a massive historical catch to this, isn't there?
Mm-hmm.
Didn't this set math back in another way?
Yeah.
Because by completely abandoning numbers to focus on lines and shapes, he creates a butterfly effect.
It is the great tragedy of Eudoxus's brilliance. His geometric solution was so perfect, so logically impregnable, that the Greeks essentially abandoned arithmetic and algebra.
Oh, wow.
For the next 2,000 years, mathematics in the West became overwhelmingly focused on pure geometry. The cultural mindset became, geometry is the realm of divine, rigorous proof. Arithmetic is just messy, practical calculation for merchants.
So the development of symbolic algebra was severely stunted because Eudoxus gave the world a geometry that seemed to solve everything.
Yes. But we can't leave his mathematics without talking about his other monumental contribution, the tool he used within this new geometric playground. The method of exhaustion.
Right. And the method of exhaustion is where we see the absolute seeds of integral calculus. Eudoxus rigorously formalized a concept initially proposed by an earlier thinker named Antiphon.
The problem was this. How do you find the area of a curved shape, like a circle? You can't measure a curve with a straight ruler.
Right, because if you try to put a square over a circle, the corners stick out. If you put a square inside a circle, there's a bunch of empty, unmeasured curved space left over.
So Eudoxus applied his logic of infinite scaling. He said, let's put a triangle inside the circle. Yes, there is empty space, so let's double the sides. Put a square inside, still empty space.
So you just keep adding sides?
Put a hexagon, then an octagon, then a 16-sided polygon, then a 32-sided polygon. You continually multiply the number of straight sides of the inner shape.
And as you do this, the straight edges get smaller and smaller, and the polygon balloons outward, creeping closer and closer to the curved boundary of the circle.
You are literally exhausting the empty space. You are trapping the area of the circle by squeezing it with a shape made of straight lines, which you do know how to measure.
And if you carry that process to infinity, the polygon effectively becomes the circle.
Using this method of endlessly shrinking the gap, Eudoxus was able to mathematically prove staggering theorems. He proved that the areas of two circles are proportional to the squares of their radii.
But he didn't stop at two-dimensional shapes. He applied this to three-dimensional volume.
You did.
Okay, wait, I need to stop you there. I can visualize putting a flat square inside a flat circle on a piece of parchment. But how do you exhaust a 3D sphere? What physical shape is he conceptually stuffing inside a globe to measure its volume?
It is a phenomenal leap in spatial reasoning. To exhaust a sphere, Eudoxus couldn't just use flat polygons. He had to use three-dimensional polyhedrons.
Okay, I'm trying to picture this.
Imagine taking a sphere and slicing it horizontally into many thin layers, like slicing an onion. He would approximate the volume of each curved slice by fitting a flat-top cylinder inside it.
Oh, like stacking a bunch of coins at different sizes inside a hollow ball.
Exactly. Stacking cylinders, or sometimes cones and pyramids, to approximate the internal volume. And just like with the circle, he would make the layers thinner and thinner, increasing the number of cylinders infinitely.
Until the jagged edges of the stacked cylinders perfectly hugged the smooth inner curve of the sphere.
Yes. By doing this incredibly laborious mental mathematics, he proved that the volumes of spheres are proportional to the cubes of their radii. He proved that the volume of a pyramid is exactly 1/3 the volume of a prism with the same base and height.
He is mentally slicing the universe into infinitely thin ribbons to prove how it fits together. It is integral calculus, achieved purely through logical deduction and geometric exhaustion 2,000 years before Isaac Newton or Leibniz are even born.
It is astounding. A century later, Archimedes would take the method of exhaustion, refine it, and use it to calculate the value of pi and the area under a parabola, achieving legendary status.
But Archimedes himself explicitly credited Eudoxus with building the mathematical engine that made his own discoveries possible.
He did.
So Eudoxus created a flawless, rigorous geometrical system to understand continuous magnitudes on Earth. But how did he apply this perfect geometry to the seemingly chaotic wandering lights in the night sky?
Well, we are transitioning now into his astronomy. And to understand what Eudoxus did, we have to understand how the ancient Greeks viewed the heavens.
Which was very different from how we view them today.
Very different. For them, astronomy was not a branch of physics. It was a branch of pure mathematics and philosophy. They weren't asking what a planet was made of or trying to calculate gravity.
Right. They believed this celestial realm was divine, and because it was divine, it had to be mathematically perfect.
And mathematical perfection, to the Greek mind, meant one very specific thing: the circle. Circles have no beginning, no end, no messy corners. The heavens had to operate on perfect, uniform, circular motion, centered on a stationary, spherical Earth.
That was the unshakable philosophical assumption.
The problem, of course, is that if you actually go outside and watch the sky night after night, it doesn't look perfect.
The stars wheel overhead in a very orderly way, yes. But the planets, the word planet actually comes from the Greek planothes, meaning wanderer. The planets are a mess.
They change speeds, they change paths. Sometimes they wander north, sometimes south.
And the story goes that Plato, acting as the ultimate philosophical provocateur, posed a massive challenge to the astronomers of his day.
He essentially pointed at the sky and said, "Look at these wandering planets. They are chaotic. But the heavens cannot be chaotic. So by the assumption of what uniform and orderly motions can the apparent motions of the planets be accounted for?"
Plato is demanding that someone save the appearances. Explain the chaos using only the divine rule of perfect circles spinning at constant speeds.
And Eudoxus accepts Plato's challenge. His response is his astronomical masterpiece, the system of concentric spheres.
But hold on. How is a guy standing on a dusty beach in Anatolia or an observatory in Cnidus doing this spatial reasoning for complex celestial mechanics? He doesn't have a telescope. What data is he even using to build these models?
This is where his 16 months in Egypt come back into play, along with the vast trade networks of the ancient world. Eudoxus wasn't starting from scratch. He had access to the astronomical records of the Babylonians and the Egyptians.
Right, they had been observing for a long time.
The Babylonians, in particular, had been observing the sky for centuries. They recorded eclipses, planetary positions, and lunar cycles on clay tablets. They tracked the movements of the planets relative to the fixed stars using very simple yet highly effective tools.
Tools like the gnomon.
Yes, the gnomon, which is essentially just a vertical stick casting a shadow, used to track the sun's exact altitude and the solstices.
They also use primitive astrolabes, sighting tubes, and water clocks to measure the exact time a specific star crossed the meridian.
Generations of priests and scholars had built up a massive empirical database of where the planets were at any given time. Eudoxus didn't need to gather all the raw data himself. He needed to provide the geometric theory that explained why the data looked the way it did.
So he takes this centuries-old Babylonian and Egyptian data, and he constructs a system of 27 nested concentric spheres. Picture the Earth sitting perfectly still at the absolute center.
Surrounding the Earth are invisible, transparent spheres nested inside one another like Russian nesting dolls.
It's like an infinitely complex cosmic spirograph.
Exactly. He assigns different numbers of spheres to different celestial bodies to account for their specific complexities. The moon gets 3 spheres, the sun gets 3 spheres.
And the 5 visible planets, Mercury, Venus, Mars, Jupiter, and Saturn, they each require 4 spheres to explain their wandering.
And finally, there is one massive outermost sphere that contains all the fixed stars.
Let's break down the mechanics of this because it's an incredible feat of three-dimensional engineering. Let's look at the moon. Why does the moon need 3 separate spinning spheres?
Because the moon has 3 distinct visual motions. The outermost of the moon's 3 spheres rotates westward once every 24 hours. That is the sphere responsible for the simple fact that the moon rises in the east and sets in the west every single day.
Okay, that's sphere 1. Makes sense.
The second sphere, which is nested inside the first one, rotates slowly eastward once a month. This explains the moon's motion through the zodiac constellations over the course of a lunar cycle.
But the moon doesn't just move east to west and through the zodiac. It also wobbles slightly north and south of the ecliptic.
Right. And to explain this wobble its motion in latitude Eudoxus adds a third sphere, nested inside the second, rotating on a slightly tilted axis.
He does something similar for the sun, assigning it 3 spheres to explain the day, the year, and what he mistakenly thought was a slight wobble in the sun's latitude.
But where this system crosses the line from brilliant into absolute mind-bending genius is how he handles the planets. Because the planets do something that completely breaks the rules. They undergo retrogradation.
Retrograde motion. It is the ultimate headache for an ancient astronomer.
It really is. If you watch a planet like Mars over the course of many months, it generally drifts eastward against the background of the fixed stars. But every couple of years, Mars will appear to slow down.
It will stop completely. Then, for a few weeks, it'll actually move backward to the west. Then it stops again and resumes its normal eastward drift. It traces a loop in the sky.
Which completely violates Plato's rule. How do you explain a planet doing a U-turn using only perfect, uniform circular motion? A circle doesn't stop and go backward.
This is the exact problem that required 4 spheres for every planet, and it is Eudoxus's greatest trick.
It is. The first 2 spheres for Mars handle the daily rising and setting and the slow movement through the zodiac. But the third and fourth innermost spheres are the mechanism that makes the whole system sing.
How do they work?
Eudoxus aligns the axis of these 2 inner spheres at a specific angle to each other, and he has them rotate in completely opposite directions, but at the exact same speed.
Let me visualize this. Imagine taking a transparent globe and melting another transparent globe inside of it. You tilt the inner globe slightly,
Okay, yeah.
and you spin the outer globe to the left and the inner globe to the right at the exact same velocity.
Yes. And if you place a dot representing the planet Mars on the equator of that innermost spinning globe, the combination of those 2 opposing tilted motions causes that dot to trace out a 3-dimensional figure 8 shape in space.
The Greeks called this shape a hippopede, or a horse fetter, because it looked like the figure 8 ropes used to hobble horses. A figure 8.
Right, so as the outer spheres carry Mars along its normal path through the zodiac, this inner figure 8 motion is constantly looping.
When the figure 8 swings forward, Mars looks like it's speeding up. But when the figure 8 swings backward, it subtracts from the forward motion of the outer spheres, making Mars appear to slow down, stop, and drift backward from our perspective on Earth.
He explained retrogradation, the chaotic backward wandering of the planets, using pure, uninterrupted, uniform circular motion. He solved Plato's challenge.
It is an elegant, beautiful, mathematical illusion. It is a testament to what the human mind can visualize without ever leaving the ground.
It is stunning spatial geometry.
But wait, if I'm visualizing this correctly, all 27 of these spheres are perfectly concentric, right? They all share the exact same center point, which is the Earth.
That is the fundamental premise of the system, yes.
But wait, if the Earth is perfectly in the center of all these spheres, doesn't that mean Mars is always the exact same distance from us?
Yes, it would.
But if I go outside in December versus June, Mars looks completely different in brightness. Sometimes it's a dim red dot, and sometimes it is a blazing red beacon in the sky. If it's always the same distance away, physically trapped on a concentric sphere, its brightness should never change.
You know, you have just independently arrived at the fatal flaw of the Eudoxian system.
So it's fundamentally broken.
If we connect this to the bigger picture, Eudoxus's successors realized it too. An ancient astronomer named Archytas of Plato pointed out the exact same problem not long after Eudoxus published his work.
The concentric sphere model, for all its geometric beauty, fundamentally fails to explain the variable brightness of the planets.
Because, as we know today, planets don't orbit Earth in concentric circles, they orbit the Sun in elliptical paths. Which means the distance between Earth and Mars changes drastically, which is why Mars gets so much brighter when it is physically closer to us.
So what happens to the theory? Once they realize the brightness problem proves it physically impossible, do the Greeks throw the whole system out?
Not immediately. They try to patch it. A later astronomer named Hipparchus, who actually studied under Eudoxus, tried to fix the inaccuracies by adding more spheres, bringing the total to 34.
And then Aristotle gets involved, right? And Aristotle makes a critical philosophical error.
He does. Eudoxus, like a true mathematician, likely viewed his spheres purely as a geometrical model, a mathematical tool to calculate positions. He wasn't necessarily saying there are actual invisible glass balls in the sky.
But Aristotle looked at this math and decided to make it physical. He argued that the heavens were filled with actual physical, crystalline spheres grinding against each other.
Oh, that is a mechanical nightmare.
It really is. If there are physical spheres touching each other, you have a massive friction problem. If the spheres carrying Mars are nested directly inside the spheres carrying Jupiter, wouldn't the spinning of the Jupiter spheres drag the Mars spheres along with them?
Exactly. To solve the friction problem, Aristotle had to invent what he called unrolling spheres. Between every set of planetary spheres, he inserted counter-rotating spheres whose sole purpose was to cancel out the motion of the outer spheres so it wouldn't transfer to the inner planets.
So how many spheres did Aristotle end up with?
Aristotle ballooned the system to 55 interconnected physical crystalline spheres. It became clunky, fragile, and utterly unworkable.
It's like patching a software bug by writing more and more convoluted code until the entire operating system crashes.
Eventually, Greek astronomers had to abandon concentric spheres entirely. They moved on to the system of epicycles, the idea of planets moving on small circles that roll along larger circles, which finally allowed the planets to physically move closer and farther from Earth, solving the brightness problem.
But even though his specific model was ultimately replaced by epicycles, Eudoxus's importance to the history of science cannot be overstated.
He proved, for the first time in human history, that you could use rigorous, complex mathematics to model the physical universe. He established the methodology that the cosmos obeys mathematical laws.
Eudoxus spent his life imposing perfect logical order on abstract shapes and distant planets. But what happens when that same intensely logical mind turns its attention inward to the messy reality of human behavior?
Which brings us to a philosophical pivot that catches many historians off guard. Because when Eudoxus turns his intensely logical, mathematically trained mind toward human ethics, he arrives at a conclusion that seems completely at odds with his own life.
According to Aristotle, who dedicated significant space to Eudoxus's ideas in Book X, the Nicomachean Ethics, Eudoxus argued passionately and logically in favor of hedonism.
Hedonism, the philosophy that pleasure is the ultimate good, the highest goal of human existence.
Let's just pause and appreciate the paradox here. The man who voluntarily walked 14 miles a day in the blazing Mediterranean sun to audit a class. The man who spent his life doing incredibly grueling spatial geometry and building mathematical axioms, comes to the conclusion that life is just about pursuing pleasure.
It sounds deeply contradictory on the surface, but you have to understand how Eudoxus arrived at this conclusion. Eudoxus didn't approach ethics like a poet writing an ode to wine or a mystic preaching spiritual asceticism.
Right. He approached human behavior like a mathematician approaches a geometric proof.
He stripped away the cultural noise, he observed the raw data of life, and he constructed a formal, deductive proof of human nature. Aristotle meticulously lays out Eudoxus's 4 main axioms for this proof.
Okay, let's unpack this ancient logical proof for pleasure. What is his first axiom?
The first argument is based on absolute universal biological observation. Eudoxus noted that all living things, without exception, both rational humans and irrational animals, aim at pleasure and avoid pain.
And furthermore, he noted that all things naturally aim at what they perceive to be good.
Therefore, his logical deduction is that if literally every organism on Earth is naturally driven toward one specific thing, that thing must be the foundational supreme good.
It's an empirical observation.
Yeah.
He's acting as a biologist here. He's saying, look at the data. A wolf avoids the fire. A child reaches for the honey.
It is a biological imperative. If the entire architecture of life is built to seek this one feeling, who are we to argue that it isn't the chief good?
Precisely. His second argument builds on the nature of how we pursue things. Eudoxus points out that people do not seek pleasure as a means to achieve something else. They seek pleasure as an end in its own right.
It is a final destination.
Right. If you are learning a trade, you are learning it to make money. If you are making money, you are making it to buy food. But if you eat a delicious meal, you aren't enjoying the taste of the food just so you can accomplish something else.
You enjoy the taste because the pleasure of the taste is the point. You listen to a beautiful piece of music not to achieve a secondary goal, but because the auditory pleasure is the final goal.
And then, for his third argument, Eudoxus applies pure mathematical logic to human ethics. He argued that any other inherently good thing you can think of, let's say justice or courage or wisdom, would be made quantifiably better if pleasure were added to it.
His logical premise, operating almost like an algebraic equation, is that it is only by adding a good that a good can be increased.
He is treating pleasure like a positive integer in an equation. If variable x is good, and x plus y results in something better, then variable y must fundamentally be a good thing.
If having wisdom is a good thing, but having wisdom and deeply enjoying it is better, then the enjoyment, the pleasure itself, is an undeniable, quantifiable good.
It is the logic of a mathematician applied to the soul. And his fourth, final argument is a philosophical observation about the nature of happiness itself. Eudoxus points out that of all the virtues and positive states in human life, happiness and pleasure are peculiar because we do not praise them in the traditional sense.
What does he mean by that? We don't praise happiness.
Think about it. We praise justice. We praise bravery. We praise a person for being disciplined. Why? Because justice, bravery, and discipline are behaviors that lead to a good outcome.
We praise the tools that build a good life. But we don't praise a person simply for being happy. We congratulate them. We envy them. But we don't view the happiness itself as a tool to be evaluated.
Because happiness isn't the tool. It's the crowning achievement. It is the finish line. You praise the hammer for driving the nail, but you don't praise the finished house. You just leave in it and enjoy it.
Exactly. Eudoxus is systematically stripping away everything else. This isn't debauchery. He wasn't advocating for gluttony or reckless thrill-seeking.
It's like he applied the method of exhaustion to human feelings.
He stripped away all the societal expectations, all the cultural norms, all the secondary goals, until the only thing left, the irreducible core of why any biological creature does anything, is the pursuit of a good feeling.
Here's where it gets really interesting, though. What made Eudoxus' argument for hedonism so incredibly persuasive, so dangerous to the ascetic philosophers of his day, was his own personal reputation.
Right, his name, of good repute.
Exactly. If some wealthy, decadent aristocrat who spent his entire life lounging on couches at banquets tried to argue that pleasure was the ultimate good, the philosophers of Athens would just roll their eyes and say, "Of course you think that. You're lazy and indulgent."
But when Eudoxus says it, a man legendary for his physical endurance, a man who traversed the Mediterranean gathering knowledge, a brilliant astronomer, a revered lawmaker, they couldn't dismiss him.
They had to take his argument seriously. His impeccable, austere lifestyle proved that he was completely objective in his philosophical conclusion. He wasn't justifying his own vices. He was reporting a mathematical truth about human nature.
So, we have journeyed through the mind of a man who refused to see the world in fragments. We've gone from a dedicated student relying on an ancient crowdfunding campaign, commuting 14 miles a day.
We've seen him bridge the terrifying abyss of irrational numbers, saving Greek mathematics by inventing a whole new geometry of magnitudes.
We've watched him choreograph the chaotic planetary spheres into a beautiful, albeit physically flawed, cosmic dance using Babylonian data and pure spatial reasoning.
And finally, we've seen him mathematically champion pleasure as the biological engine of life. Mention his lasting monuments, the algebraic curve named the Campile of Eudoxus, and the craters named after him on both the Moon and Mars.
We are looking at a legacy that is almost unparalleled in its breadth. He didn't just contribute to fields, he founded the methodologies that govern them.
Even today, thousands of years later, there's an algebraic curve named after him, the Campile of Eudoxus. If you look at the Moon through a modern telescope, there is a crater named in his honor.
If you look at Mars, the very planet whose retrogradation he mapped with his Hippopede, there is another crater bearing his name.
His fingerprints are on the foundations of how we measure space, how we observe the stars, and how we understand our own motivations. It is the ultimate counterargument to the modern compulsion to specialize.
This raises an important question, and it is a thought I want to leave you with. Eudoxus proved his mathematical theories by exhaustively observing the limits of geometric shapes. He proved his astronomical models by exhaustively mapping the limits of celestial motion.
And he proved his ethical theories by exhaustively observing the limits of human desire.
In our modern age, we so deeply segregate our knowledge. We separate STEM science, technology, engineering, and math from the humanities, ethics, philosophy, and art. We treat them as fundamentally different worlds governed by completely different rules.
We treat the objective universe as cold and calculable, and the subjective human experience as warm and mysterious.
But Eudoxus challenges us to ask, are the rules that govern the physical universe and the rules that govern human happiness really that different? Or are they just two different expressions of the same underlying geometry?
Are physics and feelings just two sides of the same equation? That is an incredible lens through which to view the world, because maybe the universe isn't a set of neatly categorized boxes. Maybe if we take a lesson from a guy walking dusty roads in ancient Greece, it's all just one unbounded landscape, waiting for a mind willing to connect the dots. Thank you for joining us on this deep dive. Keep questioning the boundaries, and we'll see you next time.